Hello everyone, this is Doug, and in this video we are going to begin our discussion about all the different carboxylic acid derivatives and carboxylic acid itself. So we're going to look at the reactivities and how we can move through the different derivatives, what the different derivatives are, as we try to do a whole wide range of reactions here. So let's take a look. So we've got a whole bunch of different types, right? So I'm just going to start at the very beginning here, right? So I've got, there we go. Acyl halides. Acyl halides are exactly what they sound like, right? We've talked about before that an acyl group is a C double bond O with an R group, and a halide is exactly what you'd think, an X, right? So here's an acyl halide. So that could be bromine, it could be chlorine, it could be iodine, it could be whatever. So a halide. We also have the anhydrides, or sometimes called acid anhydrides. Those are where you have a carbonyl and an oxygen and then another carbonyl. That would be an, I'll put in parentheses, acid and then anhydride. Again, you'll hear me just say anhydride. Many people just say anhydride. Some people say specifically acid anhydrides, but that's what an anhydride looks like. And again, you may know a lot of these functional groups already because you're in theory studied them a while ago. Esters are carbonyl with an O and another R group on it. So here you have your esters. We also have your amides, which are a carbonyl with a nitrogen on it. These groups on the nitrogen can be either H's or R groups. It doesn't matter. They can both be R groups. They can both be H's. Either way, it's an amide. What we're looking for is a nitrogen on a carbonyl. We all know what good old carboxylic acids are. Right, carboxylic acids are when you have a carbonyl but it has an OH on it. So carboxylic acid. And then lastly, we have the nitriles. So nitriles are when you have a cyano group, a C triple bond N. So this is a nitrile. This is sometimes referred to as a cyano group. If you're just talking about that, just like a hydroxyl, it's a hydroxyl group, but it makes you an alcohol. A cyano group makes you a nitrile. So you might hear those also. Now the key thing with all of these carboxylic acid derivatives, right, is that it's a carbon with 3 bonds to a very electronegative element. That's what they all have in common, right? So, sorry, let me erase that. La-di-da. Right, so they're carbons with 3 bonds to a very electronegative element. Now, in some of them, it's 3 bonds to a nitrogen, like in a nitrile. Some of them, it's 3 bonds to an oxygen, like in an ester or anhydride. Sometimes it's a mixture, like maybe bonds to O and an N, like in an amides, or maybe O and a chlorine, for example, in acyl halides. But the idea is that it's more electronegative. And that makes it more oxidized than aldehydes and ketones, right? Remember that aldehydes and ketones only had, aldehydes and ketones only had 2 bonds to a more electronegative element. So if you look at your aldehyde or ketone, you only had 2 bonds to oxygen, for example. So aldehydes and ketones are less oxidized than carboxylic acids are. So we're talking about inherently more oxidized functional groups. Now, while your aldehydes and ketones underwent addition reactions typically, right? We had things attack them and they stuck and they added. Your carboxylic acid derivatives are all going to undergo what's called an addition-elimination reaction. And I'm going to show you what that looks like right now. So let's take, for example, let's look at an acyl halide because I think it's really apparent to see what's going to happen for those. And so I'm going to take this just ethanoyl chloride here, or acetyl chloride, and I'm going to react it with something like sodium hydroxide. All right, so if I take a look at this, I've got Na+, I've got OH-, and if I look at my molecule that I'm going to react it with, I've got partial negative, partial positive, partial negative. So of course my nucleophile, right, is going to be attracted to that partially positive carbon. But now I need to figure out what's going to give, right? Because again, that carbon can't have 5 bonds. It can only have 4 bonds. And while your temptation may be to have the chlorine leave, it does not leave yet because the pi bond is so much weaker. And so what we have is that this kicks up, kind of like if it was a aldehyde or ketone. And in theory, whoops, sorry about that. So you get a CH3, C with an O minus. Now you have an OH, and now you have a Cl. Right, this would be that addition step. This is the addition part. Right, because I simply added something to that acyl halide. I just added the hydroxide. It has more stuff now. But the issue here is that, yes, oxygen is not so bad being negative, but like maybe it could drop down and make something that's more stable being negative. This is what's sometimes called the tetrahedral intermediate. And maybe I should write that also here. This is sometimes referred to as the tetrahedral intermediate. It's got a tetrahedral intermediate. And what we see happen, unlike with aldehydes and ketones, right? Aldehydes and ketones, you just protonate that oxygen and you have an alcohol there. But what can happen here is that these electrons from the oxygen can drop back down. And then you ask yourself, are any of these things, any of these 3 things good leaving groups, right? Is the methyl a good leaving group? Is the OH a good leaving group? Or is the Cl going to be a good leaving group? Now we should know right off the bat that the CH3 is not a good leaving group, right? Because that's going to leave a carbon with a negative on it. That's terrible. Too high in energy. We're not going to see a CH3 minus. No thank you. I'll just draw a red X through that. Too unstable. If it kicked out the OH, that's just going backwards. So that's possible, right? We could go backwards. That'd just be the reverse step of this in theory. Or we could have the chlorine leave, which, again, you probably are like, oh yeah, chlorine is a great leaving group. If I have the chlorine leave, that's going to leave me with CH3, double bond O now, and the OH is still there, and then I have a Cl minus. Right? So what I did was I eliminated the thing that was the best leaving group. Chloride was the best leaving group. Was the best leaving group on that carbon. So it's the thing that went. It's the thing that left. But in the leaving, right, when you have this tetrahedral intermediate and something leaves, that's just an elimination, right? Because now it's smaller. You eliminated the chloride. You eliminated the chloride. And so that's what we mean by addition-elimination reactions. All of these reactions that we see in some form or another are going to look very, very, very similar to this mechanism. This is the main mechanism, especially when you have basic nucleophiles. You're going to add something to the carbonyl. You get that tetrahedral intermediate. You ask yourself what's most likely to leave. You have it leave, and it eliminates. That's the addition-elimination reaction. So let's talk about the different reactivity between these molecules. It is a combination of electronics and sterics. I'm not going to talk about sterics too much because I've already done that in previous lectures, but obviously the bulkier the groups are, the slower the addition is going to be. The smaller the groups are, the faster the addition is going to be, just for steric reasons, just because that transition state energy changes. So what we're going to do is we're going to focus more on the electronics part. And you can look at this in one of 2 ways. You can look at this in terms of how electron rich is that carbonyl, which is a great way to look at it, right? The more electron rich it is, the better it's going to be. Or you can look at this as in how good of a leaving group do I have? How good of a leaving group do I have attached to that carbonyl? And I think that's easier for most students to kind of latch on to, so that's what I'm going to focus on here. All right, so as far as the electronics go, we're going to look at, it's a combination of how electron poor is the carbonyl and how good of a leaving group is attached. right? The better the leaving group, the more electron poor it is, the better, the faster it's going to be. So what I'm looking at here is I want to ask myself, I'm really comparing chloride versus this whole group versus this whole group, that whole group, and I'll talk about carboxylic acids later. And right, keep in mind that this, I'm talking about additions to, or sorry, reactions with the nucleophile. So I've got a nucleophile, it's negative, it's got a lone pair, right? We're talking about some sort of nucleophile. Now, if you look at this, right, chloride, we just did chloride, Cl minus is a great leaving group. And then I'm going to compare it to this as a leaving group versus that as a leaving group. And then finally the nitrogen as a leaving group. And if you look at these, right, basically what I'm doing is I'm going from most stable anion to least stable anion. Or in other words, I'm going from best leaving group to least leaving to worst leaving group, right? This is going to be, oops. This is going to be the most reactive carboxylic acid derivative to the least reactive. Just looking at leaving groupability, right? Chloride leaving, great. Nitrogen leaving, not so great. Let me see if I can align this up a little bit better. Nope, I can't. I'm just going to have to leave it. Sorry. So if I look at this, and I'll write this again on the other page, on the next page here, what I have is that that's the most reactive. Acyl chlorides are the most reactive, then the anhydrides, then the esters, then the amides. And I'm going to draw sort of a line here separating it from the carboxylic acids, because the carboxylic acids don't really react with nucleophiles very well at all, right? Because if I have a nucleophile, again, that has a negative charge on it, what happens is that the nucleophile is not going to necessarily add into the carbonyl like it would with one of these, right? Like we talked about before, if I had a nucleophile attack my acyl chloride here, like I did on that previous slide, my nucleophile would attack the carbonyl and then these electrons would kick up. But that's not what happens with the carboxylic acid. So if you looked at the far right, your nucleophile is going to not attack the carbonyl, it's simply going to do an acid-base reaction because you have a carboxylic acid. And again, good nucleophiles tend to be bases, or at least weak bases. And so your nucleophile tends to just do acid-base reactions. So I'll put, watch out for acid-base reactions. For acid-base reactions. Because again, the better the nucleophile, the better the base it tends to be. Not always, but that's a trend. And so carboxylic acids tend to just get deprotonated. Carboxylic acids do not do additional elimination reactions very well at all. We'll see them do it under really acidic conditions, but generally speaking, they're terrible. So we're looking at the electronics, right? So how good of a leaving group and how electron rich or poor is the carbonyl? Amides, like the one on the right here, they're very electron rich, right? Because that lone pair really drops in and adds a lot of electron density to the carbonyl. You look at the acyl halide on the left, that chlorine is not going to donate a lot of electron density in because it does not want to be positive. So it's a less electron rich carbonyl than like an amide is. So let's kind of put this all together so we can see it all in one place. So I'm going to give you this reactivity chart. You really, really, really want to know this, love this. You're going to use it over and over again. This is how I see any carboxylic acid derivative problem I see. I always think of this chart. Am I moving up or down this chart? So what I'm going to do is over here, I'm going to put generically, I've got my carboxylic acid. And over on the right-hand side, I'm going to draw, I was looking for something, I don't have it. I'm going to draw the acyl halides. All right, so I'll have my acyl halide, my X. Below it, I'm going to have my acid anhydrides, my anhydrides. I'm putting R, the same R for this. It could be a different R. Typically, they're the same because of the way that they're made, but they, in theory, could be different. So anhydride. Next will come esters. And then we have amides. Again, I'm putting R groups on these amides, but they could be hydrogens. They do not have to be carbon groups. And then lastly, I'll put down here the nitriles. They're kind of in their own section, but we'll add them here. And again, what I did here is I put them in order of reactivity, right? So I have most reactive up here, least reactive down here. And by reactive, I'm talking about a kinetics, right? How quickly will these react? So most reactive. So most reactive up top. Acyl halides are super reactive. And what I want you to know is that basically, and I mean, I'm saying how quickly, yes, it's true they happen more quickly, but there's also a thermodynamic component to this. Because again, like I was talking about the stability of that leaving group, right? So the idea is that you can move down this ladder, so I can turn acyl halides into anything below it. I can directly turn an acyl halide into an anhydride or an ester or an amide very, very easily. I can turn an anhydride into anything below it, but it's hard for me to, I can't turn an anhydride into an acyl halide. That's going up in energy. It's not as stable, and so I can't move up this ladder. I have to move down this ladder, and so I can move down and down and down this ladder like this. All right, so I can turn an ester into an amide in a fairly straightforward manner, but I can't turn an ester into an acyl halide in a straightforward manner. Now, in order for us to get to the acyl halides from the carboxylic acid, there's already reactions that we know. We already know reactions to turn carboxylic acids into acyl halides, right? I can add, if I want to turn a carboxylic acid into acyl halide, I can add either SOCl2, if I want my X there to be a chlorine, so if I want an acyl chloride, I can add SOCl2, or I can add PBr3 when I want my halogen to be bromine. So if I want an acyl bromide, I could add PBr3. And what's nice is I can take that carboxylic acid that I was saying tends to just do acid-base reactions. I can just simply add SOCl2. A few minutes later, it turns into an acyl halide, and then I can add whatever I want to it, and it will react. Because acyl halides are so reactive. They're so reactive. And I can move down this ladder of reactivity from here. You also want to be aware of the fact, and I might as well mention this now because we're here, we're doing it, is that I can take any of these carboxylic acid derivatives here, the acyl halide, the anhydride, the ester, the amide, the nitriles, I can take any of them and I can hydrolyze them to get the carboxylic acid back. So I can go right back to this carboxylic acid by doing a hydrolysis reaction. I can do a hydrolysis. I can hydrolyze any of these. And we have two ways, right? Two methods. Method A, you can use acidic conditions. And if you use acidic conditions, then you're just doing H3O plus, and typically adding heat, especially for things like esters and amides, which are less reactive, you're going to need to add a little heat. Sorry, that's supposed to be heat. That's a delta. Triangle. Now, you also could go basic. If you wanted to go basic, we have a base-mediated route, which is step 1, you add hydroxide. Step 2, you protonate the reaction. You protonate so you get your carboxylic acid back. And I'll show you the mechanisms of these in future videos. But you can use a base-mediated one too. The base-mediated route is superior. It's better. It's faster. It's one way. The acidic route can kind of go back and forth, and so you want to kind of be careful that you're removing what you need to remove as you do that reaction. And again, I'll show you more about that later. Base-mediated hydrolysis, for example, on esters is sometimes called saponification. It's how you make soaps and things like that. But it's really the way to go. I am going to put as a note here, as a sort of a separate note for this hydrolysis, the acyl halides and anhydrides are so reactive that even just plain water with no acid, no base, even just water, will hydrolyze them back to carboxylic acids. Back to the carboxylic acid. So you just need to add water to an acyl halide or anhydride, and it will turn back to the carboxylic acid, just like that. So that, when you're making an acyl halide or anhydride, you have to be really careful that there's no water present whatsoever, that your glassware is dry, that your solvents are dry. Otherwise, they're going to react. It's also the reason why, for example, in nature, right, in natural products, you do not see acyl halides in natural products, nor do you see anhydrides in natural products, right? So you don't see them in any organisms, and that's because, right, living organisms on this planet all have a boatload of water hanging out. So they would just react with the water. Esters and amides, for example, are much less reactive, and so you can have water around them all the time. We'll talk more later about how esters are the backbone for the triglycerides, some of your fats. So we definitely see lots of esters all over the place. They're just fats. We know that fats are fine around water. We got them in us. They're really important. Ditto amides are also known as peptide linkages. When you're talking about proteins, right? We know proteins are stable around water. We are mostly protein. We're almost entirely protein if you ignore water, but they're also very, very stable around water. Ditto nitriles. Nitriles are not as common in natural products, just because if you lose that cyano group, it becomes cyanide, and then it sticks to iron and other metals really, really well and kills them. And so, right, cyanide we know is super toxic. It kills people, but it's because it binds the metals and then makes the metals not work anymore, whatever they're trying to do, whether it's binding oxygen or whatever. So anyways, we don't see acyl halides and anhydrides in natural products, and that's because simply water, just water, will hydrolyze them back. So what is important about this reactivity chart here is that I can get from any one place to any other one place if I want. Right? I can start with the carboxylic acid. I can turn it into any one of these. I can start with any one of these derivatives and turn it back to the carboxylic acid. So I can work my way around this. So I'm going to show you a couple of examples just to give you a taste of what I'm talking about. And then in subsequent videos, we'll take a closer look at each one of these individual functional groups and go into a little more depth. So let's do a couple of examples here, right? So let's say, again, that I have, let's say that I have a CH3, let's say I have acetic anhydride, and I'm going to add NaOCH3, right, in methanol. So sodium methoxide and methanol. Now this looks to me like I'm trying to replace the group, the anhydride group here, right, this whole group. Looks like I'm trying to replace this whole group with this. So I'm trying to go from an anhydride to an ester. And if you remember from the previous slide, esters are below anhydrides, so that should be okay. That should be good. I should be fine with that, right? Because remember, you can go down that ladder, but you cannot go up that ladder directly. So if I have an OCH3 minus, I'll show you the little mechanism here, right? I can attack this carbonyl, that kicks up. I get that tetrahedral intermediate, so I have an O minus. It's still attached to this group. And I've attached the OCH3 here also. Now, when I'm asking what group will leave when the oxygen's electrons come back down, again, I'm going to look for the best leaving group. Is it going to be the CH3? No, because that's a negative carbon. Is it going to be the OCH3? That would be a negative oxygen. That's not terrible. That would be going backwards, but it's not terrible. Or would it be the other O, which is a negative oxygen, but it's going to be resonance stabilized, right? If I kick this out, I'm going to get O minus, but it's resonance stabilized, right? There's delocalization here. So that's actually going to be the best leaving group, which is why it's going to be the thing that leaves, which is going to give me my ester. So the OCH3 will stick on. This would be a forward reaction. We're good. We're good. Now, if I did that same starting material, right? So I moved down the ladder, and let me write this here, right? I moved from an anhydride, down that ladder of reactivity to an ester. That's going to work. Now, if I take that same anhydride here and I add a different reagent, all right, let's say instead of sodium methoxide, I add sodium bromide. And let's just say it's in water and not water. Let's say it's in THF. Or acetone or something like that. So I've got Na+, I've got Br-, same sort of reactivity, right? I'm going to be attracted to that partially positive carbonyl. Electrons kick up. I'm going to draw my tetrahedral intermediate. I've got the bromine attached. And then I ask myself the same question, right? I've got these electrons up on the O. Can they drop down, and what's going to be the best leaving group? Again, I've got a carbon with a methyl. That's not great. I've got a bromine, a bromide. That's really stable. That's super stable. And then I've got the O double bond, the O attached to the carbon with the double bond, right? I have that carboxylate, that resonance stabilized thing. And if I look at that, the thing that's the best leaving group, the thing that's going to be the most stable is the bromide. The bromide's the most stable thing. And so what's going to happen is, yeah, the bromide could add, but it's just going to get spat back out. We're not going to move forward because the thing that I added, the bromide, is the best leaving group, so it just gets spat out. That's different than up above, where the thing that I added, the OCH3, was not the best leaving group. It was the carboxylate thing, the O with the carbonyl attached to it. That was the most stable thing. That's the best leaving group. And remember that the leaving group ability correlates with how stable of a conjugate base it is. And you can just think about the acidity if you want, right? Carboxylic acids, for example, are not strong acids, but HBr is a strong acid. So you know that the Br- is super stable, really, really, really stable. So for this reaction down here, I would say that I get no reaction, right? I am not going to form an acyl bromide. No. And that's because, right, I was trying to go up that reactivity ladder. I was trying to go up that, right? I was trying to go from an anhydride to an acyl bromide. Right, and I cannot go directly up that ladder. I can only move down that ladder. And let me just show you, I know this video is getting really long, I'm so sorry. Let me just show you how I would make the acyl bromide from that anhydride. Just real quick. Just one more slide. Sorry. So lastly, if I did want to move up that ladder, what I would do instead was I would take advantage of the fact that I can hydrolyze this. Right? I could do step 1, simply add water, and that's going to react and give me my carboxylic acid and another carboxylic acid. Right? Where I've taken the elements of water from here, and again, I'll go over these mechanisms more in the future. I add the elements of water, and I basically I added an OH to one and an H to the other. So I've just added water, which is partially why by the way, they're called anhydrides, because you've removed water to make them. You add water back and it unmakes them. But what I can do now is I can now take this carboxylic acid and I could just add PBr3. And if I add PBr3, that's going to make my acyl bromide that I was trying to make, right? So I can just do a 2-stepper instead. I can take my I can take my anhydride, turn it back into a carboxylic acid, and then move it over to the acyl halides by using PBr3. And we're going to see this motif, this theme a lot as we go through these reactions. But I will stop because this video is getting too long. Anyways, keep that in mind. We'll start talking about more functional groups in the future. Happy studying. Please let me know if you have any questions. Best.